Hello. So up till now we have discussed two derivatives that was of free conditions, that were free damped condition and free undamped condition. The first condition that we looked upon was free undamped condition, where we used to take the value of C, that is damping constant, equal to 0, and the value of f of t equal to 0 as the force was free. Clear? Now from this session onwards we'll be moving to our forced vibration. Now what do we mean by forced vibration? That means the force that was applied initially to start the motion will remain to be applied continuously onto the system or onto the body throughout its whole time period. Clear? So that is termed as forced vibration. Whereas in free vibration it was that to just start the motion, the initial phase, the force was applied, then it was released to rotate, or you can say to vibrate on its own. But from now onwards the force will not be released, it will be acting on the system throughout its time period. So that is called a forced vibration. So the first thing that we will be looking upon is forced vibration of our SDF system, that means single degree of freedom system. So for that we will be looking upon a mathematical model. So this is the mathematical model that we will be looking upon, considering a mass m, that is a body of mass m, which is moving on a rigid surface and connected to a rigid surface via a string, that is you can say a spring constant, and a dashpot. You can say dashpot or you can say dampers. Clear? So dampers is always represented by the value of C, that is damping coefficient, and the stiffeners or you can say the springs are always denoted by the term K, that is stiffness. Clear? So the external force that was applied was Q of t, or you can say F of t. In the previous sessions we always took the value of this F of t to be equal to 0. But from now onwards this F of t will not be equal to 0. It will be always equal to F0 sine omega dash t. Clear? Our F of t will always be equal to dynamic force, and the equation for dynamic force is F0 sine omega dash t. F0 is our amplitude, sine omega dash is our resonance frequency, and t is our time period. Clear? So this will be our term that we'll be using for F of t. Now considering the free body diagram of this body, the weight force or you can say the mass will always be acting in the downward direction. The inertia force, the stiffness force, and the damping force will always be acting on the opposite direction of the applied force. So the applied force, as you can see here, is on the right hand direction. So the F of t will now be equal to F0 sine omega dash t. Clear? So as it is in the right hand direction, all the three forces according to our D'Alembert's principle, the remaining three forces, that is the inertia force, the damping force, and the stiffener force, will be acting in the opposite direction in the form of mx double dot plus cx dot plus kx. X is our displacement. The first derivative of displacement gives us x dot, that means the velocity, and the second derivative of displacement gives us the x double dot, that is the acceleration. Here, so this is the free body diagram of that stuff. Now considering a single degree of freedom damped system acted upon by the force F0 sine omega dash t, that means F of t, the amplitude of this force is F0 and the angular frequency is omega. Omega is the angular frequency. So for the dynamic equilibrium of the system, the equation of motion is just as we can see here, considering sigma h equal to 0. The summation of horizontal forces will be done. Only the F of t is in the right hand direction, that is in the positive x-axis, whereas the remaining three forces are in the negative x-axis. So the equation can be written as mx double dot plus cx dot plus kx equal to F0 sine omega dash t. Now we will be looking at an example. So considering a spring mass model, as you can see here, this is the rigid surface or you can say the ceiling where a mass is being hanged upon using the help of string. So this was the initial phase, that was in the rest state or you can say the stationary position. Now when I apply a force P in the downward direction, there is an elongation in this spring by a distance, that is x. So this is our displacement, that is x, that we already know how to find it. Clear? So if we talk about the system that the force been acting upon, so this is a delta m. Clear? That means a delta which will be on the ceiling face. Now considering the displacement, if the force P is applied in the downward direction, also there will be a significant amount of force applied on the ceiling. So that force is always termed to be delta sine omega t. Clear? This term force is termed to be delta sine omega t, and this again the displacement will be in the form of x. Now moving across, we will be finding what is this resonant frequency, that is omega dash. We have talked about the term that is omega, which was our angular frequency previously. The term omega was to be substituted as under root k by m, where k was our stiffness and m was our mass. Now we will be looking upon this omega dash. Omega dash will be coming into focus only when the force vibration condition is being given. Clear? So omega dash is the resonant frequency, the resonant frequency is the forcing frequency at which the deformation of the magnification factor Rd is maximum. So when this magnification factor Rd is maximum, that frequency is termed to be resonant frequency. Clear? So the next will be to finding the term of this resonant frequency ratio. So the resonant frequency ratio is always denoted by a small r, or it can also be termed as turning factor. From this derivation, the entire derivation is generally asked, but there is no such derivation in it. It is just a combination of definitions and equations. So you need to also remember this individual definitions, because definitions are also being asked in your examination, and for theory purposes you also need to write this whole definitions along with the equations if the entire derivation is being asked. There is not such any part of derivation in it. Clear? So the resonant frequency ratio, that is R, or it can be termed as turning factor. So R is the ratio of omega dash upon omega. That means the frequency of force, or you can say the resonant frequency divided by natural frequency of system. Okay? This is will be calling it as frequency ratio or the resonant frequency ratio, where here omega dash is the frequency of force, which is the applied external force. So the resonant frequency, or you can say the frequency of force of the applied force, will be equal to 2 pi n by 60, where n will be the number of rotations. The number of rotations in RPM. Clear? As you can see here, n equal to RPM. That means the number of rotations the body is being acting upon. Omega is, as we all know, that it is the angular frequency or the natural angular frequency, which we discussed earlier too. It is always termed as omega, and the equation for that is under root k by m. So moving across, we will be looking upon what is this magnification factor, or RD, or it is also termed to be deformation response factor. It can either be asked as explain or define magnification factor, or define deformation response factor. So RD is the maximum value of dynamic load factor. So the maximum value of dynamic load factor is termed to be as RD, or you can say magnification factor. So now what is this load factor? So for that, magnification factor can also be written as the equation, that is the ratio of maximum dynamic displacement to the static displacement. Maximum dynamic displacement, that means x, and static displacement, that means delta st. Clear? So the magnification factor can also be termed as this equation. So RD, the derivation is not been asked, or it is not been in the syllabus, so you just need to remember the equation, that the equation for RD, that is our magnification factor, is equal to 1 upon under root 1 minus r square the whole square plus 2 r zeta. Zeta is a damping ratio, which will be equal to C upon Cc, and R is our frequency ratio, which was omega dash upon omega. Clear? So this is how we will be finding the magnification factor. Now this is a magnification factor, or you can say RD. This is our maximum displacement, and this is static displacement. So now if we are making x max, that is our maximum displacement as a subject, then this will be cross multiplied. So it can be written as x max equal to delta st, that is a static displacement, and RD, that is our magnification factor. Clear? So x max can also be written as this form. So substituting it, delta st, that is a static displacement. The equation for static displacement is always taken as f0 upon k. f0 is our initial, or you can say the amplitude, and k is our stiffness. Clear? So substituting here, that is x max equal to delta st into RD. Delta st was f0 by k, RD was 1 upon under root this. So the equation for x max can be written as f0 by k whole divided by under root 1 minus r square the whole square plus 2r zeta square. So in your numericals it has been asked to find the value of Rd or to find the value of x max. So these two equations are most important regarding your numericals is concerned. Clear? So now moving across, why this magnification factor is important, or why we need to study this magnification factor? Because the value of this magnification factor is of very much interest to the designer. That means it is very much important to the structural designer. The structural designer, by just seeing the value of this magnification factor, can understand the importance of this building and can understand the dynamic forces that are being acted upon this building. How? So a magnification factor of 3, if the Rd comes out to be 3, no, so what does this number stands for? So a magnification factor of 3, that means that all the maximum displacements, forces and stresses, all the three natures, again repeating, a magnification factor of 3, that means all the maximum displacements, the maximum forces and the maximum stresses due to the dynamic load will be thrice the value obtained from static analysis. Static analysis, that means considering the body to be in rest. That means the generalized equation that we are doing in either DRCS or we used to do in MOS and SA1. That was our static analysis. But when we look upon the dynamic analysis, that is our earthquake part, or you can say when we consider external forces or vibrations into our picture, then it is termed to be as dynamic analysis. Clear? So the dynamic analysis, the displacement comes out to be 3 times the static displacement. So you can know the varsity of our equation, that how important this value or the magnification factor is. Clear? So this is the graph of it. Xm, that is our maximum displacement, that is x max, and Pm by k, that is f0 by k, that is our delta st. So this is the belonging to our term, that is Rd. So this is the graph pertaining to our Rd. So you can see that at Wf, that is our frequency omega, or you can say W dash, when W dash equal to Wn, the forcing input is in resonance with the system. Now moving across, there are 3 main things that we need to remember upon if we need to consider the numerical parts and also need to consider the derivation portion of it. So if the omega dash upon omega is small, that means Rd is slightly greater than 1. So whenever Rd is slightly greater than 1 and the amplitude is same as the static deformation, then the response of the system is controlled by the stiffness of the system only. Clear? Whereas if the ratio omega dash upon omega, that is R, is greater than under root 2, that is greater than 1.41, then the Rd, that is magnification factor, is less than 1 and dynamic deformation is less than the static deformation. Then under this case, the response is controlled by the mass of the system. And the third case is this, when omega dash upon omega, that means our R, small r, is close to 1, then the Rd, that is our magnification factor, is many times larger than 1 and the dynamic deformation is much larger than the static deformation. So under this case, whenever the dynamic deformation is very higher than static deformation, then we need to provide damping onto the system. Clear? So this is the cases where we need to see that either only the stiffness of the system will be acting and will be resisting all the external forces, either the mass of the body will be acting as the resisting forces to the external loads, or either we need to provide dampers to the system to resist the external force. So these are the 3 cases where we will be deciding that what the actual material in the structure to be used. Either the stiffness of the structure is to be increased to resist the loads, either the mass is to be increased to resist the loads, or we need to provide the dampers to the buildings to resist these external loads. Clear? So these are the 3 vital characteristics or the conditions that you need to remember upon. So now the main equation that you will be dealing upon, there is no derivation for it. So for forced undamped vibration, that means the force content is that means external force is acting on the system and the dampers are not provided. In this case, the Rd, that is our magnification factor, is represented by 1 upon mod of 1 minus r square. So this is the value of Rd which will be using when the equation is given or the question is given for force undamped vibration. The next case will be for force damped vibration. So force damped vibration, that means the external force is acting on the system as well as dampers, or you can say dashboards, are provided to the system, then the magnification factor, that is RD, will be substituted by this equation that we have already seen earlier. The equation is 1 upon under root 1 minus r square the whole square plus 2r zeta whole square, where r is our response ratio, which will be omega dash upon omega, and zeta is our damping ratio, that will be C upon Cc. Yeah? So this is the term that we will be using. Now, what is meant by transmissibility? So transmissibility is generally asked separately as your explained transmissibility and as a separate theory too. So first, what basically transmissibility means? We all know that transmissibility means the ability to transmit. It is generalized as the ability to transmit, and we all know that loads are to be transmitted from one element to other element. For example, if we talk about a superstructure, then the load or the load transfer phenomenon, first the load will be acting onto the slab, or you can say the floor. If we talk about the dynamic loading, then the base shear, or you can say the story drift, will be acting on the floor, that is to be transferred to this soil. Clear? So this will be transmitted or transferred to the beams, then it will be transferred or transmitted to the columns, and from columns to foundation, foundation to soil. So this ability to transfer the loads is called the transmissibility of the structure. So it is very important to know that how well the transmissibility of the structure is, whether it will transfer the load or transmit the load properly or not. So machines, or you can say structures even, are often connected to the foundations by springs and dampers. As we know that considering a mathematical modeling, we always identify that our body is connected to the rigid surface via strings, that is springs and dampers. The main purpose behind it is to reduce the transmission of forces to the foundation. That means it is to reduce the amount or the impact of sudden transmission. The force will be ultimately transmitted to the foundation only, but the time taken for the load to transfer from either first element to second element can be reduced during this phenomenon. Clear? So the main purpose behind it is to reduce the transmission of forces to the foundation. So the ratio of the transmitted force to the applied force, that means the ratio of the transmitted force to the actual applied force, is generally called the transmissibility of the structure. So equation, if we look upon, then it can be termed as TR, that will be a transmissibility, will be equal to FTO, that means the transmitted force divided by the actual or the applied force. Is clear? So if we look upon this, the ratio wise, or you can say the equation wise, it can be written as under root 1 plus 2r zeta whole square whole divided by under root 1 minus r square the whole square plus 2r zeta whole square. So this is the equation to be used when in the question it is being asked to find the transmissibility of the structure or the system. Clear? Now alternatively, this equation can also be written as this, but when? So alternatively, transmissibility can also be explained as the ratio of maximum mass displacement upon maximum support displacement. So whenever in your numerical problem, if it is asked in the question, or if it is the data given in the question that maximum mass displacement is given or the maximum support displacement is given, then you can use this equation. For both the cases, our FO, that is, for this case our F0, that is our applied force, will be equal to Y0, that will be our initial displacement, into K, that will be a stiffness, into under root 1 plus 2r zeta whole square. Clear? So this will be the equation that we'll be looking upon regarding the transmissibility of forces. And the last thing will be to find the phase angle. Phase angle means at what angle does the load is being transmitted to the other element or the other body. So for that we need to find the phase angle. So for phase angle is represented by phi, and it is given by the equation tan inverse 2r zeta upon 1 minus r square. So this was all about our force conditions. We discussed both the cases, that is force damped condition and force undamped condition. Just there is a minor change in the value of our RD, that is a magnification factor for both the cases, that is for force damped condition as well as for force undamped condition. And in the next session we will be discussing the numericals pertaining to our forced vibration systems. Thank you.